All right, great. All right, thank you everyone for being here, for making it the last day. And before I start my talk, I would like to have you joining me to thank all of us for the Openmolcas paper. I think so it's a long list of names, and I know only some of them, so it's nice to keep on connecting faces to names. And it was a hard work. Most of you liked the final result. That was impossible, of course, without Ignacio and Roland. And of course, without many of you with the contributions, and also with some special thanks to people like Luca and Professor Kruller, who went through the entire thing and going checking typos and consistency. That was big work as well. So now we have it, and let's hope for the best in the future of Openmolcas. Special thanks to Marco and Francesco. And Arthur for organizing this. It's perfect. And with that, I can move on now with the science. So my talk is going to be a follow-up from the past couple of years, but of course I see many new faces. So many of you might not know what I'm doing and what is my contribution to Openmolcas, stochastic classification. So I don't have much of that. The time is limited, so you are going to get a glimpse. This is only one part of my contribution to Openmolcas. An advertisement. Oscar and Arta are going to have their own talks. Oscar this year is going to talk about improvement in Fuchsia quantum Monte Carlo, which has an indirect impact on stochastic Gattatiak that he implemented and presented last year. And Arta is going to move his first steps towards stochastic Cat52, which we're going to have in the relatively near future, hopefully. So about me, I am the slave of these guys here. So they are polynuclear transition metal clusters. What it means, and I know that many of you know about it, they are cluster transition metal sites interacting with the many unpaired electron involved. So all the spin coupling, the angular momenta. And normally this coupling do not happen by a direct interaction, but they happen via this bridging non-innocent ligand atom there, sulfur or oxygen atoms. And it's quite challenging to capture the correlation into this system. There is no selected CI or truncated CI that can actually handle it. You just need to go brute force if you want to have the right physics of that. So that's what I'm doing, and hope for the best. So, by the way, this thing, maybe the more technicians in this audience don't know, but these things are ubiquitous in nature. You can find, for instance, a photosynthesis. The active site is one of the transition metal tubane. It's the manganese cluster in photosystem 2. Or if you know the nitrogen fixation problem, where ammonia is produced, that happened in that guy there, which is the active site of the nitrogenase. So all these things are extremely beautiful and extremely complicated in terms of magnetism and in terms of reactivity. All right, let's try to understand why these things are require multi-reference techniques. Okay, it's a pedagogical sort of thing. Let's imagine we have two sides, and we have a triplet on each side, and then you want to spin couple these two sides, so you know that we are going to get a quintet, a triplet, and a singlet. Now, singlet and quintet, they can fairly well describe as collinear state, which means in the quintet you have 4 perfectly parallel state, and in the singlet you're going to have antiferromagnetically parallel state. And that is all good and simple. Normally DFT can handle it, maybe the broken symmetry DFT variants, but anyway, that is fairly well represented in a single determinantal description. Now, problems start to arise when you want to describe the triplet spin state. The triplet spin state, you can conceptually think about it You have still a local triplet, but they are now interacting at a certain angle. So that's why normally it simplifies as a non-collinear state. And you can picture it with a vector model anyway. There are many ways of doing it. But if you describe the system with a single determinantal picture, all you can really do is you are going to have a singlet or a broken symmetry singlet into one side and the triplet on the other side. That's a triplet, yes, but maybe not the same that I was describing earlier. You can do the other way around, you have a singlet on one side and the triplet on the other side, or you can stay, not stay. Now, that, of course, you see that doesn't capture the corrected physics. That's the most elementary thing. One can start to increase the degree of sophistication of a methodological approach. For instance, there is non-collinear DFT. My opinion, those are numerical ways to fix up things. They still don't capture the correct physics. It's not embedded in the method. The method does not have the most elementary form of physical interaction for this system. So that's precisely, and that's about the pedagogical part, it's why we need to have multi-reference techniques. Multi-reference techniques precisely can describe this form of interaction at the level of quantum mechanics, like the way we learn in the physics class. Okay, things get, of course, complicated, as I said earlier, by this by the bridging ligands. And then they contribute to this interaction through very exotic mechanisms. The most elementary one is the super exchange mechanism that Francesco Calcagno mentioned in his flash presentation yesterday. So we want to know what is their contribution into the total energy or in the magnetism. And that is often what makes the difference in stabilizing one spin state over the other one, and therefore impacting the macroscopic effect on the magnetism of this system. So for instance, a couple of years ago, we looked into this cube rate where there is this bridging oxygen playing most of the super exchange coupling mechanism. Okay, so what do we do about this system? What we do is that a few years ago, I discovered a very exciting properties in a multi-configuration of the function. A property that allows to reduce by 10, 20, 30, 50 order of magnitudes the many-body problem. And it's based on a simple invariant molecular orbital unitary transformation that compress dramatically your many-body structure. Okay, Kasia mentioned that you want to have a wave function, and you have the head of the wave function, you have a tail of the wave function, and there are techniques to describe very well the head of the wave function. But normally for the system I'm talking about, you have a huge infinite ocean of CI expansions, equally weighted minuscule contribution into the wave function. So all these CI coefficients are 10 to the minus 20, but you have a gazillion of them, okay? So we want to solve that problem, and this strategy I'm talking about exactly does that. At the end of this simple unitary transformation, you're going to have like 5, 10, 20 CI coefficients are non-zero. All the other gazillions are 0 by theory, or they can be 0 by numericals. Okay? When they're 0 exactly, you don't need to worry about it. If we said that they are 0 numerically, then methods like quantum Monte Carlo that does stochastic sampling in the Hilbert space, even if we ignore them, will not disrupt the actual physics and chemistry of this magnetic interaction. And therefore, you get qualitatively and often quantitatively correct answers to your many-body problem. So we rely on 3 key elements. The first one is you need to have a chemically and physically motivated site reordering of parentheses localized molecular orbit. So you have atom A, B, C with orbital D, 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 M, D, and whatever. You need to sort them according to some prescriptions. And these prescriptions are now understood. Last year, I partially understood, this year, fully understood. The second point is we need to rely not on a many-body expansion used to say the determinant. That's a bit the answer to my colleague when we were discussing it briefly yesterday. You need to have cumulative spin adaptation, something that is naturally done, for instance, by the Guga techniques, where you use configuration plate function. Cumulative spin adaptation means you have electron 1, now you put electron 2, you spin couple to electron 1. Electron 3 coupled to 2 and 1. Okay, so every new electron you consider your spin couple, you need to couple the previous one magnetically. That is what we study in quantum mechanics as the Fletch-Gordon coefficient. Buga is the technological way of doing this one inside the actual many-body problem. The third point is that we might rely on graphical representation of the electronic configuration via this branching diagram. That maybe in a way or another, when you have been seeing many books talking about generators, or anyway, many body wave function and so on and so forth. Thanks to these three elements, of course, we can dig on it for days and months, but thanks to these three basic elements, we are able to produce a wave function compressor that is crucial for methods that do not solve exactly the full CI problem, but they are approximated, because the actual CI coefficients you need to optimize, they are dramatically reduced. And so that is true for FTSE, which is what we are developing currently, but it's a really conceptual strategy. You can use it on selected CI. You can use it on truncated wave function like CI or gas CI. So it's really a very adaptable strategy. Of course, requirement you need to work in the Google basis. All right, that is, for instance, one example with full CI quantum Monte Carlo. Full CI quantum, it's a chromium dimer at a certain straight geometry, 24 and 48. And if you use canonical orbital, the localized orbital, standard Hartree-Fock, CR12 you see that full CI quantum Monte Carlo has a very high instability. The blue line is that. And then eventually this simulation diverges. So you can't get a grasp on what is your result. If instead you apply this transformation, you get something like the green line. Very smooth convergence, really quick, and I can run a simulation in my cell phone, I speak, okay? So, and that is what I'm talking about. You get excellent results with inexpensive calculations. All right, that is just the tip of the iceberg. What actually is happening is that you have, this is the PI Hamiltonian matrix, the whole matrix, okay? You don't solve it exactly every day. You try to get the ground state, the few excited states, but that's how it looks like if you print it all. And you see it's extremely dense here on the left. It's highly interconnected, and that is what makes methods, again, selected CI, full CI quantum Monte Carlo, DMRG. These methods struggle whenever you have this dense representation of the Hamiltonian matrix. When you apply the transformation I was mentioning, you get that Hamiltonian matrix there, which is first sparse, the white means zeros, and you also see that it has a peculiar, unique block diagonal structure. So that means if I want to say, okay, my ground state is in the block highlight over there, then you say, well, I optimize this problem, and my wave function will contain only CI coefficients of this block. You will not have those are zero, exact zero. If you say, but that is the cool feature of it. You say, but yeah, wait a moment. If I want to optimize a wave function for an excited state, which is, for instance, in this block, then you can initialize your trial wave function in this block. And of course, the optimization will go into the minimum of this block. You will get to your ground state of this block, which happens to be an excited state. So that is a way to say, well, we open up the route towards selective optimization of excited state. And that, so on top of the 10 to the 20 speed up factor, we also have the power to have a selective CI optimizer. Okay. Very beautiful. And why is that? I can't give too much because it's too much time for that. But the root property that leads to this compression comes from a simple commutator. You have an Hamiltonian operator, which represents the chemistry, the interaction into these systems. All the interactions are represented by the Hamiltonian. And you have cumulative spins open. The cumulative spin, it's not the total spin. It's, let's say, if you have a 3-4 sides, A, B, C, D, E, F, G, so on and so forth, it's a partial spin. So let's say A plus B. And you calculate the spin of that quantity. Yeah? If you prove that SA plus SB squared, which is the partial spin operator, commute with Hamiltonian equal to 0, then you know, that means that these two operators admit common eigenbasis. So that implies that you can have eigenbasis of the Hamiltonian operator that can be separated based on the eigenvalues of the partial spin operator. And that's why, for instance, say, okay, what is the block then? Then the first block is, for instance, Fa plus Sb equal to 0. The total spin is, I don't know, a singlet, a triplet, a quintlet, but we are talking a partial spin. It's about only the coupling between A and B. So when you do that, that's what it is. So each block is a different block in the partial spin program. And so that's why I was saying you can use branching diagrams, because these exactly represent that. Here I have a state site A, B, and C. Each one is a spin 3/2. So electron 1, electron 2, electron 3 leads to a 3/2. And I'm trying to couple them to lead to a quartet, a spin state as a total. But you see, the way we reach it is go from a singlet, a triplet, a quintet, a sextet as an A plus B. And if this one commutes with Hamiltonian, then I will have 4 different blocks, 1, 2, 3, and 4, based on the eigenvalue of the partial spin. That is the core. I hope it gives you the idea of all this. And therefore, the Hamiltonian carry the idea of the chemistry. The partial spin is what makes the trick of the plotting, and that the spin depends on the ordering. So if you have A, B, C, you need to do it cumulatively. So it's A plus B. If you sort them and you say, now I have A, C, B, so I reorder the order, then the cumulative will apply to A plus C. And you can show that, for instance, one ordering commutes to the Hamiltonian, another ordering does not commute to the Hamiltonian. The one that does not commute will have a very dense matrix. The one that commutes to the Hamiltonian will have a very sparse matrix. Very cool. Okay. We generalize that. So now, I will not go into this detail, but now you say, okay, I got this cubane. How does it look like? You look at it and say, okay, it's this sort of Hamiltonian, have them there. Then you can prove that you can have accumulator commutators. Let's say the site A plus B, A plus B plus C, and then they commute, and then you have all these blocks. Or you can say, well, no, my system doesn't look like this one. The natural system look like this one. It has a little bit of distortion, different thing. Then you say, okay, well, I can't commute with this one, but maybe I still can commute with this one. So you know what is the ordering you want to give such that you reach the maximal compression and you can understand that. Of course, that one is depending on the nature. So this is like, it's when methods understand what the nature is doing. Yeah? It's not going to force anything. The way I like to describe it is like that. So this is called anamorphosis. Anamorphosis is you go around the sculpture, you see what exactly the sculpture is if you stay specifically in one point. Here we do the same. You have this ocean of many body expansion. You don't see anything. Of course, we have techniques, spin densities, but you don't see really anything with your eyes. But if you move, transformation of the orbital area, you will reach a point where you have a 1 CSF. And then in 1 CSF, we are stupid enough that we can understand 1 CSF, and that's great. I call this technique quantum anamorphosis in analogy. Of course, mathematically speaking, this analogy is a little loose, but I hope we give you the idea. And we used it in the past. I will skip that part. Here, I was doing anisole for cubane, and I was targeting ground state singlet and the highest state singlet of the low spin manifold by skipping all the intermediate spin state. And I could do it because my matrix was block diagonal. I could optimize the rest of the excited state without doing multi-rote approach. And this was a 44 in 33 active state, and I could convert into 1 million walkers, which, as I said, is like half an hour simulation. Okay, it doesn't always happen. Doesn't always happen, right? If your system is a covalently system like poly-AC, of course that wouldn't apply because you don't have the concept of local spin. Yeah, so that is true for magnetic system, which are the system that is labeled on, right? So perfect. Recently, with Sandra Luber and Roche and Han, we did this fantastic work on this cobalt erbium cubane. People thought that my idea was true only because I take advantage of high symmetric systems. Like you say, you take a perfect cube. Then that's not true. It's something different. It's about the spin. It's about the locality in the many body expansion through the spin coupling thing. The way here we have erbium, which of course is different from the cobalt, and the geometry is highly distorted. And yet we could do a 56 in 56 active state optimization, relatively cheap. I mean, I'm not going to lie. This is still like it's a long project. So each calculation a couple of days, and you need to have a pile of them. So it's like a 3-month or 6-month approach. And you need to hope that the active space is stable, But in this case, in this picture, I want to show 3 results. The first one is that we find that it's a ferromagnetically ordered system. So the high-spin state is the ground state. And this one is given by first, the 56 and 56 calculation bare and simple. Or if you do, for instance, a 12 in 12, which would be the minimal active space, then you top it up with MCPDFT, you get the same result. And if you do a 56 and 56 and you top it up with MCPDFT, you still get the same result. So I thought I have 3 methods that are telling me that the high spin state is the ground state. I can't be sure, but that's what I can say. Okay? CAS52, I did 12 in 12. And CAS52. CAS52, this is in the literature. I reported it, other people reported it, and you can all experience it. When you do CAS52 will overstabilize the low spin state in this case. So you see an anti-ferromagnetic ordering. And I did a trick. I say, okay, I remove the virtual orbitals, the frozen orbitals, and I keep my 56 in 56. And which I know the result because I have exact solution from Fusiago to Monte Carlo. And in that 56 and 56, I take a 12 in 12, and then I do the CAS52, but the CAS52 is only able to see the 56 and 56. So the best CAS52 can reach is my 56 and 56 solution. And still, you see the anti-ferromagnetic bias. Okay, so that is kind of it's also for the porphyry, and it's something similar. It's a way you prove that where the CAS52 is missing. Of course, we don't know if it's a particle excitation, charge transfer, we don't know what it is yet. I'm doing that. But that's the way you say, okay, CAS52 fails, and that is mathematically, well, numerically proven, okay? So we trust this result. Why do we care about calculating speed ladder? You care because you can have a link to experimentalists. The first data were to experimentalists, so I thought this could be relevant for them. We can have, for instance, temperature-dependent effective magnetic moments simulated and experiment. They are pretty much in agreement, and that is beautiful. Recently, we found that is maybe the right community to have this slide. Recently, we found that the same idea can be applied to traditional luminescence complexes with one metal center and a ligand. We have with Oscar, we have this exotic state, which I best can describe as an intramolecular singlet fission state. The way you want to see it is you have a triplet in the ligand and you have a triplet in the metal, and they are coupled antiferromagnetically. That is a singlet fission state. But if you don't order the orbitals the way they are, but rather you sort them in the canonical ordering, so you have first the pi, then you have the p, and then you have the pi star, that ordering will give you the mass around the wave function. So you wouldn't see that actually is a singlet fission state. So again, ordering is key to have a simple mind understanding of what's going on in your many body. Okay, conclusions. This quantum anamorphosis is a general concept. It's not a methodological thing. It has methodological biases, and you are forced to use Google and so on and so forth. But you can use it in transition metal clusters. You can use it in photoactive luminescent transition metal complexes of traditional things. And you have unprecedented accuracy, the enormously reduced computational cost. This idea must be picked up by selected CI community, must be picked up by quantum computing, because you need to use it. I mean, it's a must, okay? That said, future directions, you need to explore the permutation of phase. That is, meaning you need to permute your sites. My slide with a lot of Hamiltonians helps to reduce that thing, but still you might need to have an exploration of the permutational sites. That can be done. I have worked in place with another student at Stuttgart, and it can be explored using genetic algorithm techniques. You have different cost functions. You can use different model Hamiltonian. It's fun, and I'm enjoying it a lot. And the question is, can we also apply quantum anamorphosis for systems where this commutator does not hold, let's say, a covalent system? We are looking into it. So even if the commutators is not zero, but you might see that one commutator is smaller than another one. Can we kind of cast this information into that. Again, the genetic algorithm is the way I'm trying to sort things out, and of course, theoretically, like analytically speaking. And with that, I would like to thank the group, especially Oscar and Arta, who are, as I said, they are contributing into the Molcas, but not with this topic. But nonetheless, they also help a lot into discussions. Ali also for discussions in what could be good for FTSE 1 Monte Carlo, how we can tailor things to each other. And Niklas, Daniel, and Maru, who are also contributing into analysis of this compression, and Sandra and Roten, who helped me to prove that this thing can actually be used for general purposes as long as they are magnetic systems. And recently, I would like to mention also the collaboration with Ivan and Francesco Calcagno, and we see the same pattern, which is very beautiful. And I hope we can keep on pushing with this contribution collaboration, and of course, all of you for the kind of thank you.
Just to clarify, your model is works on the stiffening normal as well.
Yeah, of course.
But then how do you optimize normal importance? Like the steep SH plus SB. You mean the electrons that are optimized on A and B sides?
Yes, yeah. Of course, it is phase dependent. So if you're you that's why we localize the orbitals, so they become orthogonal. Huh? It's not particular to distinguish the orbitals they're sitting. Particularly distinguish the type.
So then
the
one that is all that.
Correct.
Do you like this patient?
As I said a couple of times, if there are covariant prevailing systems, you don't gain much of this. So that's what we believe right now. Maybe next year will change my mind. But that's what my feeling is, that if you don't have any spin to take advantage of it, nothing. The same applies to the next. That's partially true if you're like a charge transfer. What do you do? Because if you're in a neutral thing, then you are looking at a certain type of Hamiltonian. When you look at the charge transfer state, you're looking at a Hamiltonian. How do you solve that? Are you going to have like a TJ model Hamiltonian or the Hubbard Hamiltonian because the Heisenberg might not work anymore? Yes. So it's a system dependent.
Yeah.
Okay, well, I invented this. I can say it. Okay. It's good. Thank you.
The last speaker for the session is Giovanni Office. About
Okay, so do you hear me well? Yeah, usually I have a loud voice. Okay, so hi everyone, I'm Flavia and I am a postdoc here in Bologna, and today I will show you some very recent results that we got thanks to the latest available analytical Caspity-2 gradients that allowed us to have some very stable and very accurate dynamics. But also this will give me the chance to show you one of the latest features that we have implemented in Cobram, that is the software that was developed in our group, that is fully integrated with Molcas, and that thanks to these new features, allows to reproduce with high fidelity transient spectroscopy experiments. So the molecule under investigation in this case is not a big one, it is acetylacetone in the gas phase. It has been experimentally determined that in the gas phase, this molecule exists almost completely in the enolic form, thanks to the stabilization given by the strong intramolecular hydrogen bond that forms the ring. And going to the electronic structure, the photoexcited acetylacetone. So when you excite acetylacetone, you bring it to the pi star state of the enolic form, which is the second excited state. The S1 is dark instead. And what is triggering the photochemistry in acetylacetone is the difference in the hydrogen position of the hydrogen involved in the hydrogen bond between the ground and the bright excited state. So in the ground state, but also in the first excited state, actually, the hydrogen, it really belongs to one of the two oxygen, okay? The structure is more asymmetric. Instead, in the bright state, the hydrogen is shifted towards a more symmetric geometry. And so this places the hydrogen out of equilibrium, and this triggers the molecular motion and then the photochemistry. So the experimentally detected photochemistry for gas phase acetylacetone is a photoisomerization, actually a rotamerization, so a breaking of the intramolecular hydrogen bond, and the formation of radicals, so fragmentations. Actually, this is a two-step, they are not parallel, but first you have the rotamerization and then the fragmentation. But the photochemistry does not take place on the singlet states. You've seen that their structure are all planar, so the planarity is not broken in the singlet. Actually, the photochemistry takes place on the triplet state that is populated from the dark S1 through intersystem crossing. So for this molecule that has been already studied a lot, it is now accepted that the deactivation pathway is first of all an ultra fast deactivation of S2 that populates S1 in less than 100 femtoseconds, and then the dark state lives longer, and then you populate the triplet through intersystem crossing, and then you have the photochemistry. But also the direct pathway has been detected, but it is a minor pathway. And this deactivation in the gas phase has been probed experimentally several times. You find several studies in the literature, and of course, in time, the resolution of this experiment has increased. And up to now, the highest resolution reported is around 100 femtoseconds, a bit less than 100 femtoseconds. So up to now, a clear tracking, a clear experimental determination of the S2 lifetime is still missing. Okay, so this is what misses in this picture. So if you are an experimental chemist and you develop a very nice and highly resolved setup for a transient experiment, acetylacetone might be a good candidate for you to assess your setup if you are able to track the deactivation of S2. And among the different probing techniques, transient photoelectron spectroscopy in this case is particularly suited because the ionization spectra of the ground state and of the excited state are clearly separated. They are far apart in the energy window. So it's very good to probe the excited states. And that's exactly what they did in Milan, in the group of Prof. Mauro Nisoli at the Polytechnic of Milan. They have set up this, prepared this very nice and highly resolved setup to perform a transient photoelectron spectroscopy in the gas phase. And they've reached a very high resolution of about 20 femtoseconds. And they have exactly tested it on acetylacetone, obtaining this very nice and highly resolved spectrum in which at the early time scales, is clearly visible a signal around 4.5 eV that decays within 50 femtoseconds. It has almost completely disappeared. So, okay, this is the feature. And so they asked for some theoretical support for these simulations, and we were very happy to help them because we were also looking for a case study to assess our new spectroscopy simulation tools that we have introduced in Cobram. So first of all, we took acetylacetone and we performed some molecular dynamics, exploiting the accurate analytical Caspity-2 gradients. And on top of these dynamics, we have tried to simulate the spectroscopy experiment, okay, at early times. So this is just the most accurate dynamics reported up to now. In fact, was at the CAS-SCF level because Caspity-2 dynamics was still too expensive to do. So we've done all of this through Cobram, which is a code developed in our group some time ago. It is completely free. You can download it from GitLab, and it is completely interfaced with Molcas. Cobram was originally designed to perform QMMM calculations, and for this it interfaces several softwares. For now, Amber, and for the QM part, Openmolcas and Gaussian, but we wish to expand this library of available softwares, and it can do a lot of things, from static calculations to optimizations of geometry, but also conical intersections. It also does dynamics with surface hopping, and we are continuing to add new features, and today I will focus on the spectroscopy simulations. So now I recognize that my sponsorship to Cobram becomes a bit weak. I'm trying to sell you this QMMM software with a gas-paid study, but believe that all these nice features are working, and they do very well also in QMMM. Okay, so this is the level of theory for our simulations. We did CAS-STF with 10 electrons in 8 orbitals, and then extended multi-state CAS-PT2. And with this level of theory, we were able to reproduce the absorption maximum with extremely high accuracy. And then we also looked for ionized state, simply removing one electron from our orbitals. And through Wigner sampling, we were also able to reproduce quite well the experimental ground state ionization spectrum. Then we went to molecular dynamics. We ran more than 100 trajectories at the same level of theory that I've shown before. I have to say that Cobram by now does not allow to simulate intersystem crossing, so we cannot simulate the long timescale dynamics, unfortunately. But since we want to focus on the S2 signal for the early timescales, this is fine. Okay, it works well. And we've done this trajectory sampling from Wigner distribution, starting on the bright state and using the analytical CAS-PT2 gradients. This is just one trajectory as an example, but the dynamics is very stable and also very fast. It looks very accurate. So on top of these dynamics, so this is the population dynamics that comes out. So in agreement with what they see in the experiment, apparently the bright state decays very, very fast. I mean, at 100 femtoseconds, it is not zero, but okay, the population has almost completely dropped. And the decay happens very close to the Frank-Condon point. So there is this conical intersection, S2 to S1, in the immediate vicinity of the Frank-Condon point. So then we moved to the simulation of the transient spectroscopy. In Cobram, this is done in a two-step process. So first of all, you have to use this utility, which is called Cobram Rampam Probe. It has several options that are documented, but basically what it does, it takes your trajectory or each of your trajectories, and at regular time intervals, you calculate the higher states. They might be optical excitation if you want to do UV visible CAM probe. They might be ionized state, as in our case. They might be core excited states if you want to do core X-ray absorption. So this makes the utility quite flexible for different kinds of spectroscopies. And then once you have done these calculations, the second part is this other utility, Cobram PAM-probe spectrum, which also has several options, basically to choose the window for your spectrum, for your spectrum, and the broadening for the signals. And basically, this second utility digests the data produced from the first part and produces the spectrum looking at the energies and couplings with the active state along your trajectory. Okay. So this is what we obtained for acetyl-acetone, our simulated spectrum. If we compare the early time scale with the experiment, we were very, very happy to see that at first sight, the agreement is remarkable. It's very nice. But also if we go to a more accurate analysis, so in this plot, I'm showing the position of the peak of the signal in time. So where is the main peak of the signal in the binding energy spectrum? And you can see that comparing the theory and the theoretical and the experimental traces, they peak at almost at the same energy along all the first 200 femtoseconds. So also the quantitative accuracy is, in this case, it's very high. And moreover, if we focus our analysis just on these slides, which is the S1 signal, the signal coming from S1, which shows some coherent oscillations also in the experimental spectrum. In fact, if we focus just on this part of the spectrum, you see that there are oscillations, and of course they are more clear in the theoretical spectrum, but also the experimental one shows some peaks. And already from this plot, if you look at the positions of peaks and valleys, you see that they match quite well. In fact, if we Fourier transform this, we get that the theoretical and experimental traces, they peak at the same frequencies. So we were very happy to see that from this test, our tool for the spectroscopy simulations seems to work quite well. As I said, this is still work in progress, so there are still some analysis that is left to do, both from the chemistry and scientific point of view. We wanted to now, so we've seen this coherent oscillation, and now we're trying to address these oscillations to some molecular motion, coherent molecular motions in our trajectory. And also from the software, from the code development point of view, there are still some improvements that are on our wish list for COBRAM. First of all, COBRAM is now, we have recently implemented the reading of the analytical Caspity-2 gradients, but the NACs are still missing. So we are working to implement also the reading of analytical Caspity-2 non-adiabatic couplings to improve the dynamics, the hopping algorithm, also to possibly optimize, for example, the conical intersection between S2 and S1, and also possibly to include triplet state and intersystem crossing in COBRAMs with some approximated algorithms that are available. So there is still something to do. With that, I conclude. So I would like to thank my supervisors here in Bologna, Marco, Arthur, but also all the other people in the group. Of course, our collaborators in Milan, in the group of Prof. Mauro Nisoli, in particular Stefano Severino, who performed the experiment and with whom I am in a close collaboration for the analysis. And of course, all the people that worked in the COBRAM project from the beginning, but in particular here, I would like to thank the latest developers, Matteo and Davide, who have done really a great job in updating and extending the COBRAM capabilities. And of course, thank you for your attention.